Good morning, everyone. I want to welcome you to another class. Of course, I've decided to spare more time on the univariate linear regression because, it's highly crucial to understand the multivariate version. And that's why what we actually going to do today, will still be on the material that I uploaded on Wednesday. Because the fact, if you understand the univariate linear regression, understanding the multivariate version will be very easy. So I introduced you on Wednesday to how we model relationship between the response variable and some predictor variables. I'm actually going to continue from there today. Now, what we are trying to do is if I have a response variable y and some explanatory variable x1, x2 up to xp, depending on the number of explanatory variable that I have, our intention is to decompose variation around the response to explain an unexplained variation. I'm actually going to say this. There exists a total variation around the response variable. Okay. So variations are total variation. Okay. Total variation around y. We want to decompose that into explained variation, and unexplained variation. Okay, the total variation around y, we want to decompose that into explained and unexplained variation. Now, because our intention is, to explain, when we want to explain, is we're seeking causal goal. We're seeking causal goal. We're seeking causal goal is to explain the true relationship between the response and the predictors. Now, what I'm showing you right now, take a look at this guy. When you hear sum of square total, is the total variation around response variable y. Okay, you can see the sum of square total that actually centered on y. There's no x. When you hear sum of square regression, that is what we call explained variations. Explained variation. That is sum of square regression. And as you can see here, you are subtracting the mean of the response from the predicted. The y cap here is predicted. It means you've already fitted a model. You know the values of x. You have predicted for y. The difference between predicted and the average is, the square of that, the sum of that, that's what we call explained variation. Now, when you hear sum of square error, the sum of square error means unexplained variation. Unexplained variation. Okay, which means variation that cannot be explained by the model. And that is the reason why model is not the same as reality. Okay, model can't explain everything. The gap between reality and the model is the sum of square error, which is going to be y minus y cap, the actual response, minus predicted response squared. You sum all of that, that is unexplained variation. In a typical regression model, we want to try to minimize the sum of square error. Okay, now when we're doing this, go ahead. Okay, so I can call that sum of square error, or I call that sum of square residual. Sum of square residual when samples are involved. Sum of square error if I use the population of data, but the file remain, they still mean the same, except that one for sample, one for the population. Yeah. Okay, now with that, we're also going to have associated degree of freedom for sum of square total. Please pay attention. For sum of square total, the degree of freedom will be n minus 1, the number of observation minus 1. For sum of square regression, the degree of freedom is p, which is going to be the number of explanatory variables. For sum of square error, the degree of freedom is n minus p minus 1. And there's another thing I wanted to pay attention to. When I had this guy together, when I had the sum of square regression to sum of square error, that give me sum of square total, which means explained variation plus unexplained variation, that will give us total variation. The same thing also applicable to the degree of freedom. If I had this together, mathematically speaking, the degree of freedom for regression, the degree of freedom for error, adding them up, will give us the degree of freedom for total. Please pay attention to that. Now, I've given you how, the sum of square variation, the one for the total, the one for the regression, the one for the error, with their corresponding degree of freedom. Now, if you want to have them in matrix form, because this is going to prepare us for multivariate regression, how do I write sum of square total? Because if you take a look at what I have here, this is writing that in a scalar form. How do we write something like this in a matrix form? That is what you see here. This is in a matrix form. Now, how do we write sum of square regression? In a matrix form, this is the matrix form. And don't forget what the H represent, heart matrix. H represent a heart matrix. Then the sum of square error in matrix form is what you are seeing here. Okay, now this is the mathematical way to partition the variance. I told you the other time, take a look at this. If I started with a sum of square total, which is the total variation, okay, mathematically speaking, I can split that into explain and unexplained. So what I'm trying to show you now is the way that we did in decomposing the sum of square variation around the response into various components. Pay attention to this. What did I introduce here? Please pay attention. What did I introduce? I introduced a y cap. Look at that. I introduced negative y cap plus y cap that can cancel out and still go back here. And after that, when I'm here, okay, what I actually did, please pay attention. This is very crucial. When I do the grouping, this guy and this guy is going to be synonymous if I call that guy A and I call this guy B. Okay, now if I say A plus B in mathematics, right? One second. In mathematics, A plus B all squared will give me what? A squared, right? Plus B squared plus 2AB. You remember that from algebra. 2AB, okay? That's exactly how we got here. Do you see how we got here? The first one, we started with that summation y minus y bar squared, which is the sum of square total. We introduce negative y cap plus y cap, negative 5 plus 5. It's like we've introduced nothing. Then we do the grouping. Y minus y cap, let it be A. Y cap minus y bar, let it be B. Okay. When I have a plus b squared in mind, it's going to be a squared b squared plus 2ab. That's exactly what we have here. That is what we have here. So this is more or less like I'm having a squared. This is more or less like I'm having b squared. This is more or less like I'm having 2ab. Now, when you take a look at where we are right now, okay, when we take a look at where we are right now, so when we take a look at where we are right now, this guy here is a sum of square regression, the first part. The second part is a sum of square error, okay? Now, when you take a look at this part, this guy here, y minus y cap is the residual, right? When you take a look at that guy, and let me tell you this, if I multiply this guy out, if I have y cap and e cap minus y bar minus e cap, okay, the facts remain that they're going to give us 0. And this is how I know if I make this to be a constant, if I make this guy, as sum of residual, okay, we expect that sum of deviation is 0. Does that make sense? Because of that, the whole of this part is going to go away. We're going to be left with this. And what has happened? This is how we decompose the total variation around the response variable into explained and unexplained variation. If we're not able to do this, there is no moving forward. There is no way we'll be able to test for adequacy of the model. I'm going to say that again. Without decomposing the sum of square, the total variation around the response into explained and unexplained variation, there may not be a way to conduct an F-test to investigate how adequate is the model. You're going to see that playing out. Now, do you know what we just did right now? What we just did right now that we're able to decompose. That is what we program. We program that in R. For instance, I actually, the other time we look at the effects of cylinder transmission and that's on a response variable, probably MPG. Okay, we look at the effect of 3 variables on MPG. Okay, I'm quickly going to remind you. These are the predictors. Okay, these are the predictors. So these are the predictors. What I show you on Wednesday, MOD, if you want to fit that in now, you say MOD equal LM, right? Equal LM. Okay, now the MOD equal LM, then in parentheses, your response variable MPG, okay, your response variable MPG on the cylinder, okay, on the cylinder, plus the AM, plus the carb, okay? And by the time you do the summary of MOD, you have the results. But what are we doing here? After getting the results, I needed to look at another code, ANOVA into MOD. What do you think I want to achieve with ANOVA into MOD? What I want to achieve with ANOVA into MOD is to test the significance of the overall parameters in the model. Now, what is going to be my hypothesis in this case? Let me say this. ANOVA is a splitting or breaking down of total sources of variations around the response variable into various components. I'm going to say that again. Analysis of variance is the splitting or breaking down or partitioning of the sources of variation around the response into explained and unexplained variation. And that is the reason why, if I want to test this hypothesis in R, you know what the H naught is talking about? The H naught is saying that we don't need covariates. Beta 1 equal to 0, beta 2 equal to 0, beta 3 equal to 0. Okay, it means that H naught represent intercept model. Intercept model. Okay, now the alternative is saying at least one is not true. And the only way to investigate that is to do ANOVA into MOD. Now, let's take a look at results. Now, in looking at the results, so I'm going to show you, uh, what you're going to use. Now, from this, we're going to check the p-value associated not with the individual, but with the general one. Okay, you're checking the individual with the general. I mean, you're going to check with the general one, but the one that I provided here is just to, it's just going to show you, it's showing you, uh, the one for the individuals. Okay, the one for the individual is actually giving you that each of that is significant. And this is also to showcase to you we got different kinds of sum of square, type 1, type 2, and so on like that. So this is using type 3 sum of squared. So what I've done here is the decomposition of the response around, I mean the variation around the response. Okay, more information on that. But what am I driving at? What I'm driving at, if I'm able to split the total variation around the response into explained and unexplained, then I will be able to determine the R squared. Because the R squared is actually what here? Is the ratio of explained variation to the total variation. Explained variation is SSR, total variation is SST. What does that mean? It means we want to know out of 100% variation in the response, how much of that the model was able to explain. I'm going to say that again. Out of 100% variation in the response, how much of that the model was able to explain. So what you see now, if I know my SSR is unexplained. I'm sorry, it's explained variation, and my SST is total variation. So the ratio of explained to the total variation multiply by 100, because at the end of the day, we're going to multiply by 100. It has to be in percentage. We want to know how much percentage variation, in the response the variable was able to explain. R squared is different from correlation. R squared here is called coefficient of determination, but R is correlation. Correlation is just going to tell us the degree of relationship between them, whether positive, negative, or not, whether weak or strong, or moderate. But the coefficient of determination will give a further information about how much percentage variation in the response the model was able to explain. And that was why I said R squared lie between 0 and 1. Okay, when you do the ratio, because it is expected that if when I have R squared and I have sum of square regression divided by this, the denominator is always going to be larger, because the denominator is the sum of square variation around the response, is the total. And that's why I normally said ratio of explained variation, the ratio of explained variation to the total variation. Of course, this is going to be bigger than explained because there's always going to be unexplained. No matter what we do, there's always going to be unexplained. Does that make sense? No matter what we do. Therefore, we expect r squared to be between 0 and 1. But whatever you get, you multiply by 100. Okay. Now, let me now say this. Larger r square value do not necessarily imply a good model. We're still going to talk about that in situation where we have so many predators. Okay, if you are adding predators, if even if the predator doesn't contribute or the predator is nuisance, the r square is going to go up. Okay, but we use r square at least when maybe simple linear regression, or you have two predators. The moment you have more than two predators, r square cannot be relied upon. Okay, we need to adjust for that, and that's going to take us to adjusted r square. Can you see that? Can you see that? Okay, when do we adjust for our r square? When the number of predators is large. Okay, and some statisticians believe that it is if it is from 3 and above, 3 predators and above, then we need to adjust. We need to adjust for r square. In adjusting for r square, what are we doing? Well, the only thing we're doing in adjusting for r square is we're adjusting for the degree of freedom. Now there's something I need you to see. Initially, what was the formula for r squared? Now, take a look at this. This is the formula for r squared. I can also split it. How do I go from the first to the second? Please pay attention. This is how I go. Do you know the explain is the same thing as S total minus SSE, right? Explain is also the same thing as that. Okay? Then divided by SS to SST. So if you do SST divided by SST, 1 minus SSC over SST. So you can see the second one was derived from the first one. Now, here, this is an r square that is not adjusted. If I'm going to adjust, I only need to adjust with the degree of freedom for error and the degree of freedom for total. Now, I need you to see now, this formula is going to change when I get to adjusted. Please pay attention. When I get to adjusted, that formula is going to change. And you're going to see if we're going to be dividing by the degree of freedom. What do you see? 1 minus SSE over SST. What do we do to SSE? We divide by the degree of freedom for error. What do you see with the SST? We divide by the degree of freedom for total. What we have right now is no longer r squared, but r squared adjusted. So we actually adjust our r squared to avoid overfitting. Overfitting. We normally have overfitting in a situation where there are so many predators in our model, and that will lead to over parameterization, and that will cause overfitting. And the overfitting means your model will do great with the training data, but will perform poorly with unseen data, which means your model cannot be used to generalize. I'm going to say that again. Overfitting occur because there's so many predator variables. Okay, you have a problem of overparameterization. Okay, and of course, which means there are some predator variables that may not necessarily contributing, which you have added, and when you add them like that, even though r square is going to go up, r square is sensitive to addition of predators. Whether predator is nuisance or great, r square is going to go up. And that is why there is need. If you don't adjust that, if you want to base your metric of evaluation on r square in such situation, you're going to mislead. Okay, you're actually going to mislead. We don't want to mislead. Okay, and that is the reason why I said capitalizing on spurious effect present in the noisy data. You know what make data to be noisy? When there are so many nuisance variables in the model that don't necessarily need to be. Okay, now when I divide, please pay attention. When I divide sum of square error by its degree of freedom, it becomes the estimated variance. It becomes the estimated variance. Okay? And when I divide the sum of square total by its degree of freedom, it's become the variance of y. Variance of y, like variance of the response variable. Variance of the response variable. Please pay attention to that. Now, we use arrow adjusted, like I said. Okay? Now, in case if you really want to know how to estimate sy squared, that I call which is just going to be a sample variance of y. That's why you see divided by a minus 1. Can you see that? A sample variance of y. Okay. Now, uh, if you want to get sum of square, the sum of square regression that I talk about, the sum of squares in R. Okay, these are the code. If you want to get sum of squares in R, and if you want to get R squared and adjusted R squared, okay, these are the code. Okay, in R. Okay, and I needed to say something here. R squared was 0.811, but adjusted R squared is 0.7833. You can see R squared is actually telling us that the module explained 81%. Why the adjusted R squared? Say no, it's not 81%, it's 78%. The one we can rely upon here is adjusted R squared. We can rely on adjusted R squared when the numbers of predator is more than 2. If it is 1 or 2, we can still go with the R squared, conventional R squared, that's no problem. Okay, now I actually want to move right now into where we are now. How do we obtain the method, the maximum likelihood estimate using a function? For instance, I actually want to derive a formula, for my regression parameter. We want to estimate B. So we want to use the method of maximum likelihood. If you want to use the method of maximum likelihood, we have to have it in mind that the response variable for linear regression, the assumption is that the response variable follow normal distribution. I told you on Wednesday, when error follow normal distribution, the implication is that the response variable also follow normal distribution. Now, if I have my model is actually y equal xb, okay, plus the error, right? SB plus the error. Now what I'm trying to say, okay, y follow normal distribution. If I find the mean of y, okay, it's going to be xb. Why? Because the mean of the error is 0. That's not going to be in the module anymore. That's why you see xb. But the variance of y is sigma squared. I told you in matrix form, it's going to be sigma square identity. I told you on Wednesday, the both error and response variable follow normal distribution, but they have different means. Okay, error follow normal distribution, the mean is 0. But here, y follow normal distribution, the mean is xb. But they both have the same variance. Error follow normal distribution with the variance of sigma squared and also the response variable. Now, this is how to write the density function for normal, the normality that I just talked about, using the idea of this, using using I have f of y equal, if y in a classical statistics is y follow normal distribution. With this, I have f of y equal 1 over square root of 2 pi sigma squared, then y minus mu over sigma all squared. Now, this is in a classical statistics class. Okay, we have that. But you know what? Our mu here is expected value of y. And if y is xb plus the error, and I take expectation of both sides, okay, expectation of that, okay, I'm actually going to have this plus expected value of error. And expected value of error, don't forget the other time we said follow normal distribution with a mean of 0. So this guy is 0. So which means expected value of y is this, and this is mu. And that's why in this distribution, wherever I will see mu, we're going to put xb. Okay, now this is writing it in scalar form. You know, if I want to rewrite this guy in a matrix form, I'm actually going to have instead of me having y minus mu squared, it's going to be y minus that and y transpose and the other one. Do you see now? Okay. Now, if I have this as, and as you can see, if I have a distribution written in this form, this is for one for or a response for individual. This is for individual. Now, what you see here, you can see you can see n. Where does the n come from? Please pay attention. Where does the n come from? Now this is where the n comes from. If I want to use the method of maximum likelihood, then I need to have a joint, the product. I need a product of that. If I want to get a product of that, this is going to be 2 pi sigma square. You know, initially this is supposed to be raised to power half because of that. And by the time this one goes, I'll raise to power minus half, but this is going to be minus n over 2. Okay, because I'm seeking the joint. And here, I'm actually going to have this summation, okay, y minus that, all squared, where I start from 1 to n. Now, what I have here is what we call the joint PDF. The joint PDF is called the likelihood function. Likelihood function. So we need to get the joint PDF whenever we want to use the method of maximum likelihood. The joint PDF is more or less the product of the PDFs in n terms, and that is the reason why you can see here I got 2 pi raised to power minus n over 2, then sigma that raised to power minus n over 2, and all of that. Does that make sense? And when I'm writing it in a matrix form, I don't need a summation. So this is right, writing this in a matrix form, you can see 2 pi raised to power minus n over 2, sigma square raised to power minus n over 2. Then when I come here, I don't need this, but there's a sigma squared here that is going to come down here. Then how do I write y minus mu all squared? Y minus mu squared in matrix form is going to be y minus mu transpose y minus mu. And what have I plug in? Mu equal xb. Now, if mu equal xb, if you take a look at what I have now, this is multiplicative in nature. Because what we're looking for now is to optimize that. We want to optimize that. We want to maximize. We're seeking maximization problem. Now, it may be difficult to maximize a multiplicative because a joint PDF is multiplicative. Now, for easy differentiation, we're going to introduce a log. We are introducing a log. Okay, log of that. Log of that is going to give me this guy. Can you see what I've done? The log, introducing a log to that is going to give me that. Okay, it's going to give me that. Okay, now you're actually going to see here, there's a particular one that has disappeared after introducing the log, because the one that, if you take a look at, if you actually take a look at this part, right? So that part does not contain B. What is B? B is what we're looking for. B is the vector of regression coefficient. And that very part does not, because after splitting, after taking the log, and we want to do differentiation with respect to B. And a term that is not contained in B will be regarded as constant. And when you differentiate a constant, it's going to be 0. Does that make sense to you now? Why we cut that part? You can see that part is not showing. And that very part is what I refer to as plus C. Does that make sense? This very part here is what I'm actually referring to as plus C. Because it's a constant, it does not depend on B. Is there any question here? Okay, now this is the what we now need to do now. We are set to differentiate. We need to differentiate now. Differentiating this guy now with respect to B. And I'm going to show you the result of the differentiation. Now, which means we are seeking to maximize. Why do I say B lies in P plus 1? Okay, the intercept and the P number of parameters. You know, we have intercept B0, then B1, B2 up to BP. So that will be P plus 1. Then at the end of the day, when you do that, you're actually going to have this result. Now, it means in what we program in software, okay, what we program in software to estimate the parameters of linear regression is actually that guy. Okay, that is what is programmed behind the scene, which is the formula. We got that through, the maximizing the likelihood, the joint likelihood function. Okay, now the next that I'm actually going to showcase right now, I actually want to move because of my time. I want to go into estimated error variance. Estimated error variance. Okay, estimated error variance is very, very crucial in statistical analysis. But how do I get it? It's easy. Okay, if I know the sum of square error, I will just divide the sum of square error by its degree of freedom. You know, if you take a look at this guy, that guy is more or less like n minus p plus 1, right? What is p plus 1? The p plus 1 is the number of explanatory variables and the intercept. Does that make sense? So that is so the estimated error variance is dividing sum of square error by that. And this is how you get, this is in matrix form. Okay, take note of that. And of course, it's an unbiased estimate of the sigma squared. Okay, we have a population variance, sigma squared. So this can be used to replace that. And we have shown that it's an unbiased estimate for that. Go ahead. Represent. Okay, P is the number of explanatory variables. You know, if I have P number, okay, for instance, I have 3 explanatory variables in a model. P is going to be equal to 3. But the numbers of parameters I'm going to estimate is not 3 because there's also going to be intercepts. So the model is going to be B0, B1, X1, B2, X2, B3, S3, 1, 2, 3, 4. And that's why we say P plus 1. That makes sense, right? Okay, so it's always going to be, we're focusing on model with intercept. The plus 1 is adding the intercept. Does that make sense? Okay. Now, let me now say this. If you take a look at this, there's something I want you to take notes. This is sum of square error. If I divide sum of square error by its degree of freedom, it becomes estimated error variance. Estimated error variance is the same as the mean square error. Mean square error. Estimated error variance is the same as the mean square error. Okay, because the mean square error is when you divide the sum of square error by its degree of freedom. Please take note of that. That is very crucial in analysis of variance. Okay, Gonna keep moving. Okay, but let me tell you this. When you use the model, let's say for instance, you go back here. If you go back here, if you go back here, and after taking the log, you differentiate with the respect to sigma squared. We're looking for sigma squared. The sigma squared here is going to be called MLE sigma squared. You remember the other time we talked about MLE covariance and sample covariance? The sample covariance is divided by n minus 1. The MLE covariance divided by n. You remember? Also here too, if I want to go by this and I want to get a sigma squared, it's going to be MLE sigma squared. And that MLE sigma squared will be biased. Biased in the sense that instead of divided by n minus 1, it's going to be divided by n. I'm going to show you now. It's going to be this guy here. This is what you're going to get at the end of the day for MLE sigma squared. When you look at the log likelihood function and you differentiate with the respect to sigma squared, you set to 0, you solve for sigma squared, this is what you're going to get. It's going to be divided by n. But the other one was not like this one. We said this is an unbiased estimate. I think I said that the other time. Okay, I think I'm gonna keep going. Okay, now take a look at what I have here. Please, I need you to pay attention. I said this is going to be the MLE of sigma squared is going to be biased. Okay, now how do I know it's going to be biased in classical statistics? When the when the expectation of an estimator when the expectation of an estimator is equal to the value of the population parameter, it is said to be unbiased. But the moment it is not equal to the value of its parameter, then it is biased. So this is how we know. You can see that is how we know. What is making that to be biased is n minus p minus 1 divided by n. That is what is making that to be biased. Otherwise, imagine if this guy, imagine 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 if this guy is not there. If this guy is not there, you know what happened? Then if it means this guy is going to be equal to sigma squared, that will be unbiased. But what is making it to bias is this. So the bias, so what is causing the bias is this. But let me tell you this. So that is an acknowledgement that maximum likelihood estimation approach is biased. But let me tell you this. Maximum like despite the fact that it's biased, it benefits from asymptotic normality. Asymptotic. 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 When sample size is large, the bias will convert to 0. Okay? And which is what I'm trying to do here. Please pay attention. This is theoretical. Okay? Now, that is exactly. Now, if you take a look at this, I want to do something now. Okay? You know, this one is what I have. If I want to measure the amount of bias, okay? You know, the one that is unbiased is this. The one that is unbiased, please pay attention. The one that is unbiased is when this equal sigma square, right? Now, this is bias. If I want to know the amount of bias, then I should be ready to subtract this from this, which is what I'm doing here. Can somebody see what I'm doing here? I want to know the amount of bias. Then I'm subtracting that. Then after subtracting that, this is what I got. But let me tell you this. When sample size is large, when n tends to infinity, what happen? When n tends to infinity, what happen? When the denominator tends to infinity, the whole of that will tend to zero. The whole of this will tend to zero when n tends to infinity. So when sample size is large, then the variance becomes zero. Even though initially the variance is not zero for maximum likelihood, but when you take a sufficiently large sample, the variance will tend to zero. You know what? You know that property? That property is called consistency in statistics. Consistency of an estimator. Okay, when sample size increases, the variance of the estimator converges to zero. That's exactly what we mean. Now, these are very crucial points that I said I'm actually going to spare my time on. Okay. Now, here we are comparing sigma squared and that. Now, take a look at that. The first one is the MSE, the mean square error. And the second one is the MLE sigma squared. This guy here, the one that is unbiased. This one here, the one that is biased. The first one that is unbiased is when you are dividing the sum of square error by its degree of freedom. I'm going to say that again. The one that is unbiased, okay, the one that is unbiased is called MSE, mean square error. Okay, you divide the sum of square error by its degree of freedom. The one that is biased is the one that you derive from the maximum likelihood estimation technique. Does that make sense? Okay. That's exactly what you need to be able to know the difference between the two. Okay. Now, I need it. Oh my God. I need you to pay attention. We want to have a justification here. The justification here is that if you take a look at what I have here, it is very obvious that if this is this, okay. Now, if you take a look at this, 1 over n minus p, minus 1, compare that with 1 over n. Which one is going to be smaller? Which one is going to be smaller out of the two? It's the first one that will be smaller. Now, this is what I'm trying to say. I want to prove that, sorry, it is this one that will be smaller, the second one. Because if I have 1 over 1, let's say this, 1 over 10 and 1 over 8. Can you see that? 1 over 10, 1 over 8. Which one is smaller? 1 over 10 will be smaller. You know that? So now what we're trying to see here is this. We are trying to say that the mean square error, we're comparing the mean square error with the MLE, and we're trying to say the MLE will be smaller than that of that. Okay. After, I want to believe when you have a large sample size, that is actually going to happen. And that is why in statistical analysis, in analysis of variance, we make use of that. Now, this is how you compute that in R. How you compute the one for the MLE and the one for the mean square error. Look at the MLE here. MLE gives 6.63, but look at what the other one gave. Which one has a smaller value? It is the MLE. Can you see that? Because the MLE benefit from asymptotic normality. So take a look at that. So if you really want to know, there are several ways to compute the MSC. You can see here from we are getting the same value. All of this is to compute the MSC, the mean square error. But how do we compute the MLE? Is this. Now, if you compare them, you're actually going to see the MLE is smaller. Oh, my time is up. My time is up. I think I'm still going to continue from this on Monday. Is there any question? Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone. Okay, bye for now. Oh, so you didn't see that, right?
No, because it's the
Which video
Yeah,
are you looking for?
it's the entrance of two vector mean. When you click on it, it's the same audio and slides as this one.
So the same audio,
Yeah, it's the exact same as the previous one.
yeah, because I didn't complete one. I started. Okay, now you know what you need to do. Uh, is that way you can share me this two link
Yeah,
and you put the message. I will read it and I pick something out.
Okay, perfect. Thank you.
Oh, okay, okay. I will bring it on Monday. Are you gonna be around on Monday?
No, I'll just get on Monday.
On Monday. Okay. So you can send me a message. But anyway, I'm gonna bring all to class.
Okay, Monday then?
Yeah.
Okay, thank you.
You're welcome.